Alright, today we're going to continue for the classification of fluid flow and then the Bernoulli equation. So just recap what we have learned yesterday class. We learned how to derive the velocity and the acceleration in the form of Eulerian point of view. So Eulerian point of view consists of space and time. Thus, in the velocity, we need to represent in the terms of x, y, z, time, as well as in the acceleration, we present in terms of time and space. So we have done example 1 on how to get the acceleration when the velocity vector is given, and then we solve for the question B, the velocity component in direction of 40, which is we use the dot product. And C, the direction of maximum acceleration. Right? So this is your homework. I hope you will do because this will test your understanding. Now we proceed to the classification of fluid flow. So three-dimensional, the velocity vector depends on three spatial coordinates, which is x, y, z, and also time. This is in Eulerian form, description. So a stagnation point, a point at which the fluid does decelerate and come to the rest. So that means now we introduce you with the stagnation point. That means the fluid initially coming from the top and then decelerate, okay, and then go here. The fluid that is directly from the top will stop immediately. That means the velocity is equal to 0 at the final speed. This term we call as a stagnation point. So in one-dimensional flow, the velocity vector depends on one variable, which is this one. Okay, R. U is depends on the radial, one variable. That is a 1D. That is why one variable. A developed flow in which the velocity profile does not vary with respect to the space coordinate in the direction of the flow. Alright. So for the developed flow, that means this is the pipe. The flow will be like this, the same. Okay. The the velocity profile, this is what we call a velocity profile. The velocity profile unchanged throughout the pipe. This is considered as developed flow. The flow already developed. We call a matured flow. A uniform flow is opposite to the developed flow, in which the fluid property are constant over the area. So for example, this is the situation. This is the pipe. We consider as a uniform, that means the velocity profile is the same. Okay, that means the speed here, V1 is equal to V2. Okay, it is the same throughout the radial direction. So now we go to the inviscid flow. Okay, this is more on the viscous effect, which viscous effect do not significantly influence the flow. Okay, does not lah. Viscous effect does not significantly influence the flow. So for example, we have the aerofoil shape from cross-sectional view. The outside of this airflow is we call as an inviscid flow, as you can see here. Alright. However, for the viscous flow, it is basically inside the boundary layer. So the viscosity are very important. So you look at here, when we have the aerofoil, for example like this, surrounding of aerofoil, we categorize into boundary layer. Okay, we have a boundary layer. Why we have the boundary layer? Because we want to differentiate between in viscous flow and viscous flow. So outside of this is in viscid flow. Inside of the boundary layer is a viscous flow. That means the effects of viscosity is very important. Alright, and then a viscous flow is either laminar or turbulent. That means within the boundary layer, we have either laminar or turbulent flow. So what are those? Okay, so laminar flow with no significant mixing of particle. No mixing of particle, but with significant viscous shear stress. Turbulent flow, on the other hand, irregular flow and random variation. For example, a steady turbulent flow in which the time average physical quantity do not change in time. Okay, this is a velocity in the y-axis over time in the x-axis. As you can see, for example, the water, okay, this is your pipe system. Okay, this is a pipe. And then we have a water flow throughout the pipe. Okay. Alright, this is water. Okay. And then you put one sensor, maybe a probe. Okay, you put a sensor. Sensor is a velocity sensor lah. Alright. So you measure over time. So what you can see is that the velocity is keep changing over time. This is what we call as a turbulent flow. It is a mixing of flow. Okay, the flow is random variation. So normally people, when they want to solve the turbulent, they simplify the process. So how they simplify? They use the time average. So from this one, they convert into average. So they will find the average velocity. Okay, in order to simplify the calculation. So this is we call as a RANS turbulent model. Renault average Navier-Stokes turbulent model. If you learn CFD, okay, computational fluid dynamic, if you are interested in CFD, okay, you will see a lots of RANS turbulent model in your software, okay, in your equations. Okay, so to understand clearly, let's take a look the analogy of the people walking to the work. Okay, walking to go to the office or school, for example. So now we have two kind of situation. This is a very structure of flow. Okay, people moving very slow. Okay, traveling in a flow direction orderly. This is orderly manner. It move in the same direction, orderly manner. However, at the bottom side, it is random. Random movement of people at different speed, at different direction. So you can see this going here, and this from here going here. And then different pace, okay, different speed. So this is mixing of flow. We call this as a turbulent flow. And this is laminar flow, as you can see in the water, in the pipe system. So, if the Renault number is greater than the critical Renault number, then the flow is turbulent. Alright, this statement means there is a way to differentiate between laminar and turbulent. Right? So how to differentiate? It is very difficult just to look at by our eyes. Okay, so we have the value to differentiate between laminar or turbulent. So since the lamina is very slow motion, okay, the traveling at low speed, wait, yeah. Okay, class, sorry for the delay. Let's proceed. This Lamina and Turbulent, you can see directly from your eyes, okay? However, to differentiate them, we need to have the value. So, when the value is more than 2000, it is considered turbulent. So, this 2000 refer to the critical Renault number, RECRIT. That means we call it as a critical Renault number. The value is around 2000. This is for different geometry, if different case. For example, for rough wall pipe, we must make sure the critical Renault number around 2000. If it is more, it is turbulent. However, for the parallel plate, right, the critical Renault number is 1500. For the flow on the flat plate, it is 3 the power of 3 multiply with 10 the power of 5. Okay. So this is the critical Renault number that differentiate whether the flow is turbulent or laminar. Alright. So you can look at this flow on the flat plate. Alright. This flow, you can see clearly from here, starting point to here. Okay. The flow, basically the Renault number is less than 2000. If the flow from here to here, the Renault number is more than, sorry, not 2000. The 2000 apply for the first case. Okay. It is 3 the power of 5. Okay. And this Renault number is more than 3 multiply with 10 the power of 5. So within the Lamina and Turbulent, we have the transition. Okay. It is a transition. It is mixing, either it is Lamina or Turbulent. It is both mixed. So of course, it is difficult to analyze clearly the transition. So up until now, the scientists only discover, differentiate either it is laminar or turbulent. All right. So this is a boundary layer. Remember, the boundary layer is a layer within the region that the viscous effect is very important. So let's take a look at example 3. The 2 meter diameter pipe, as shown here, used to transport water at 20 degrees Celsius. What is the maximum average velocity that may exist in the pipe for which laminar flow is guaranteed? Alright. So before we start, what is what we call? This is the case of pipe. What do you think the critical Renault number for the pipe? Do you still remember? Okay. You can see we have the rough wall pipe. It is around 2000. This critical Renault number around 2000. Renault number have the equation. Okay, VD over nu, right? This is kinematic viscosity. This is velocity. This is pipe diameter. Alright. Another equation of Renault number, rho VD over mu. This, on the other hand, is dynamic viscosity. Alright. So, by using the equation, the question asks the maximum average velocity that will cause the laminar flow. Okay, In order to achieve the laminar flow at the maximum before reaching to the turbulent, we must use the critical Renault number 2000. From this one, 2000, we will get the V maximum of laminar. Alright, so applying the equation, Renault number equal to velocity diameter over nu, kinematic viscosity. Rearrange, we will get V equal to Renault number nu over diameter. So, Renault number, just substitute the Renault number 2000 multiply with nu, which is 1 multiply with 10 the power of negative 6. This directly refer to table at temperature 20 degrees Celsius. Alright, you will find nu, kinematic viscosity. Alright, divide with the diameter of the pipe, which is 0.02 meter. So you will get 0.1 meter per second. So 0.1 meter per second is the maximum speed for the water. Okay, for the water to flow. More than this speed, it will become turbulent. Alright. Now we go to the final one, which is Bernoulli equation. Alright, the Bernoulli equation will come out in your test one. Okay, not only Bernoulli, it is up until Bernoulli lah. Alright. Okay, a relation between pressure, velocity, and elevation. Valid in region of steady incompressible flow where the friction is negligible. Equation typically used in the flow region outside the boundary layer and wicks. Alright. So this Bernoulli equation use the relationship between pressure, velocity, and elevation. So it is only valid outside the boundary layer where the incompressible flow or incompressible flow is negligible. Alright. This is aerofoil. Example, this is aerofoil. Right. Okay. And then we have the flow. So this is the flow streamline. Alright. So inside this flow, we have we call a boundary layer. Okay. The boundary layer is very close to the surface. And here we have the wick, which is the circulation of flow. It is like a chaotic flow. Alright, we call it as a wick. So the Bernoulli equation is not applied within inside the boundary layer as well as at the wick section. It is only applied outside of the boundary layer. Maybe it is applied at this point or this point, or maybe this point. Okay, Bernoulli equation acceptable. So the acceleration of fluid particle, you can see here, the motion of particle and the path it follow described by the velocity vector as a function of time and space. With steady flow, all particles that pass through the same point follow the same path. Okay, this is the steady flow. So the speed of the particle relate to the distance by v equal to ds over dt. This is usual, yeah. The change of distance over time, we get the velocity. For example, we have the small element of flow. Okay, like this. We have the element here. Okay, this element. Alright, this element moving moving this way. Alright. So now, let's say this distance as a ds. Alright, and it flows from here directly, straight line. Okay, it become acceleration in s direction. This is the streamline, follow the streamline. This is acceleration in terms of normal line, which is normal to the flow. Alright, so this is the streamline. Alright, for example, like this. To make, okay, this is like a fluid particle. It follow the streamline. Okay, and this is ds. Okay, I take it out and I put this way. Okay, so the streamline acceleration now has two parts. The first part is as, which is follow the streamline. And the second part is an, which is the direction to the normal. Okay. Normal direction. Normal direction to the streamline. Alright. So, an here is basically we can use v squared over r. This is the r means the radius of curvature. Alright. So, as is due to the change in speed along streamline. Right? And then an is due to change in position. If an should be small. If an equal to 0, that means the particle move in the straight line. Okay. So here again, we can show you in the Eulerian point of view, space and time. In order to get the v, okay, this is the dv. Velocity is a partial derivative of v over partial derivative of s. This is ds. plus partial derivative of v over partial derivative of time dt. This is in terms of velocity. However, in terms of acceleration, okay, in terms of acceleration in streamline direction, dv over dt, which is equal to partial derivative of s, partial derivative of v or partial derivative of s, ds over dt. Alright. Plus partial derivative of v over partial derivative of t, dt, dt. Okay, this we can cancel out, 0. And if this is a steady state, that means there is no change of property over time. This can be, okay, cancel out. Alright. There's no change of velocity over time. Alright. And there is a change of displacement over time lah, because it is moving. Okay, because it is accelerate. So now the equation become, okay, partial derivative of v over partial derivative of s v. Okay, this is we simplify into v. Alright. Doktor, kenapa doktor mute? Kenapa doktor mute? Okay. Hello? Alright. Sorry ya. Okay, let's start with the derivation of Bernoulli equation. The first, we have the x-axis and the z-axis, and then this is the fluid element, and this is the streamline of the flow. Alright, so here, the distance from here is here to ds. Alright, the fluid element flow. Maybe it will flow from this region to this region. Okay, we call as a ds. Alright. So, okay. This will have the, okay. Alright. This will have the force. Let's say we have the force. Alright. Which is PdA. Alright. The pressure from this side, and also we have the force from the other side. Pressure plus the change of pressure, because different location will have different pressure. That means the pressure here, we need to plus the pressure at the change of here. Multiply with the A. Okay. And then we have the wake. Okay, the wake of the element, which is downward. And then let's say we have the normal line, which is we have the angle theta. All right. So this is in the streamline direction. Okay, now let's apply the Newton law. Newton. Okay, second law. In S direction. The streamline direction on a particle. Okay. Moving along the streamline. So the summation of force in the streamline direction equal to mass multiplied with the acceleration in the streamline direction. So here, let's make a triangle. Okay. This is the streamline direction, ds, right? Okay, this is the change of z, dz. And then this is dx here. Okay, I try to make this way. And this is, of course, this is theta, the same as this theta. So, let's do the summation of force, which is positive to the right, negative to the left. Alright, so we start with PDA, which is here, minus with this one, facing to the left. Okay, P plus dP multiplied with the area. Okay, the area, the cross-sectional area of this. And then minus with W, the wake. Okay, because now the wake, we integrate, we separate into streamline and the normal direction. So let's say the wake here, we separate from here into here and into here. So now we consider the weight in the streamline direction. Of course, it is minus W sine. Okay, we must use sine theta equal to M V dV ds. Okay, where do I get dV ds? Okay, from this one lah. This is acceleration. Acceleration in streamline direction. Okay. So, from here, okay, we know that sine theta basically dz over ds. Okay, sine opposite over hypotenuse. So we can substitute in this equation. Okay, now let's substitute. Alright, we try to okay, and ds here we try to expand. Yeah. Okay, we try to multiply here. Okay, multiply here. Multiply here. So P, right? P, okay, okay. I think better I try to expand this one. Okay. So PdA minus PdA. You can see I try to expand this one. And expand this one. Minus dP dA W sine theta, I try to substitute. Sine theta with dz over ds mv dv ds. P dA cancel. Okay, cancel with this one. So we only have negative dp dA minus w dz. Okay, ds equal to mv dv ds. Okay. Okay, now we can see that, okay, as usual, okay, where the weight is equal to mass multiplied with gravity. So the mass here is equal to rho multiplied with the volume. So it become weight equal to rho v g. Okay. So in order to get the volume, okay, you can see that the volume in order to get the volume of this, which is the multiplication of, how to get the volume? Of course, the cross-sectional area multiply with ds. Okay, dA multiply with ds. So I can substitute. The weight is equal to rho dA ds g. Okay, and then I can substitute directly to the weight. So negative dP dA minus the weight, which is rho dA ds g dz over ds equal to the mass. Okay, mass we can substitute rho here. Rho volume is dA ds dv over ds, and then we have v also. Sorry, we have v dv ds. Okay, I think I want to simplify. ds ds. So negative dp dA equal to rho dA, okay, g dz, okay, equal to rho, okay, dA v dv. Okay, now we got here this equation. So what to do next? We can rearrange the equation. Alright. Okay. Now we have dA, dA, and dA. Why don't we cancel A? Okay, I want to cancel dA because dA is the same. dA, dA, and dA. Okay, I write it down. dP rho G dz equal to rho V dV. Okay. And then what should I do? I rearrange. Okay. I rearrange this one first. Okay. dP. Okay. Over rho. Okay. Because this one I want to divide all with density. And then remove negative lah. Alright. And then plus, okay, this one plus V dV plus G dz equal to 0. Alright. Now we see we in the form of differentiation. Okay, this is applied to one fluid particle. Let's say if we want to apply to the whole fluid particle, what should I do? What should we do? If we want to apply to the whole of fluid particle, what should we do, class? Any idea? This is differentiation. Very small, small fluid element. If I want to apply to the to very big pool, so what should I do? Any idea? I need to integrate. Okay, remember we need to integrate in order to get the solution for the whole area. Okay, so we do the integration. Okay, integrate both sides lah. So we will get integrate with differentiation, cancel lah, P over rho. Plus this one integrate V squared over 2. Okay. Plus G Z. Okay. So equal to constant. Okay. Why equal to constant? Because if you do all the integration, it will have the constant. So the constant you move to the other side, it is constant. So that means P, this term, okay. That means after you integrate, you will have the constant along the streamline. So, for example, this is the flow. Okay, this property, pressure, velocity, and Z is the same as this property. Let's say this is constant. This constant one is same as this constant two. Okay. So we can write when it is involved 2 points. When it is involving 2 points, as I mentioned here, point number 1 and point number 2, on a streamline, we can use P1 over rho plus V1 squared over 2 plus GZ1 equal to P2 over rho plus V2 squared over 2 plus GZ2. So this term is this is the flow energy. This term refers to the kinetic energy. And this term refers to the potential energy. Okay. What is the energy equation? Anyone knows? Okay, what is the energy equation for kinetic? Kinetic energy equation. Do you still remember? Kinetic energy equation? Class?
Ada 3, doktor.
Okay, a kinetic energy equation yang simple, half m b squared. Betul tak?
Betul.
Okay, potential energy equation?
Potential dia ada rho GH. Dia ada H. Dia ada G.
Okay, mgh. Okay. Potential energy is mgh. Okay, you notice that both have mass and mass, right? Okay, you can see this is half b squared. This is gh. So you can see here, v half and gz. However, we don't put mass because we consider this as the unit. Okay, the potential unit potential energy, that means it is divided with mass. Okay, that means it is without mass. We call as a, what we call it? Unit energy. Okay, it is divided with mass. So all this basically is the unit energy. Alright. So let's try example. Okay, take a look this example. So the wind reached a speed of 144 km per hour. Definitely this is not SI unit. Okay, 144 km per hour. You need to convert into meter per second. Compulsory. Calculate the force acting on the window, the dimension given, facing the storm. The window is in the high-rise building, so the wind speed is not reduced to the ground effect. Use the density of the air to be 1.27 kilogram per meter cubic. So, let's say we have 1 and 2 points. This is point number 1. And this is point number 2. So, upon reaching at point number 2, the velocity at point number 2 equal to 0 because it is at the stagnant. It is stopped immediately because of the obstacle by the window. However, the velocity at V1 is equal to 104 km per hour. And then the window, let's say, at the same elevation. So H1 and H2 is equal. So the question asks, find the force. Force acting on the window. So the force equal to P multiply with the area. Right. So we must know the pressure acting at the window, which is pressure number 2. Pressure number 1. So to solve this, let's first convert velocity 1 to SI unit. So V1 is equal to 144. This is kilometer, which is multiply with the 3, divide with 3600 second. You will get 40 meter per second. This is the conversion unit lah. From kilometer per hour to meter per second. You will get 40 meter per second. Alright, now apply the Bernoulli equation. Okay. So apply Bernoulli equation at point 1 and 2. So I want to apply Bernoulli equation, which is V1 squared over 2G plus P over gamma plus H1. You may notice that it is quite different, but basically it is the same lah. Okay. For this case, I try to divide by G. Okay. So P1 over rho G plus V1 squared over 2G plus Z1. It will be the same as P over gamma because this is gamma plus V1 squared over 2G plus Z. This is also Bernoulli equation. Okay. That is why I'm using this one. The same thing. Equal to V2 squared over 2G plus P over gamma plus H2. Okay, what we cancel? We cancel. H, H2, H1 cancel. Velocity 2 cancel because velocity 2 we know for sure it is stagnation point. Okay, upon the impact, the velocity at the particle reaching 0. So what we left? We need to find P2. Our ultimate goal, what is P2? So to get the P2, rearrange the equation, it will come rho V1 squared over 2. Okay, you rearrange lah everything. It will be in this equation. Okay, you simplify, you will get this. Okay, now substitute rho. It is given. Rho of the air 1.27 multiply velocity 40 meter per second. It is squared over 2. Okay. So you will get the answer is 1016 Pascal. So, okay, from here, right, I need to find the force. The force at 2, which is pressure at 2 multiplied with the area of the window. So pressure at 2 is 1016 multiplied with the area. If you look at here, the area will be of the window will be like this. Okay, this is 0.9, this is 1.8 meter. So just multiply. You will get 1.646 Newton or 1.646 kilonewton. That's it. Okay, any questions so far?
Doktor, yang velocity tu, yang 40 square tu doktor dah siap-siap tukar kepada MS eh?
Betul.
Okey, baik.
Nampak ni saya tukar. From 144, this one, this is kilometer per hour, convert into meter per second. Make sure using SI unit ya, class. Okay. I think simple kan? This one. Just apply P1 and P2. Okay, now we go to the last point lah. Okay. The stagnation static dynamic pressure. Okay. When we involve the Bernoulli equation. Okay. Bernoulli equation state that the sum of the flow, kinetic and potential energy, this one yeah. The flow refer to P over, which one Okay, P over gamma. Okay, use this one. P over rho. Okay, kinetic is equal to V squared over 2. And potential is Gz is constant. Okay, that means the combination of this lah is equal to constant. Kinetic and potential energy can be converted into flow energy and vice versa. So that means in order to find the pressure, you can move all this to the other side. You get the flow energy. Okay, cause the pressure to change. So let's write. Okay. So from here, I try to write again pressure over rho plus V squared over 2 plus Gz equal to constant. Okay, so multiply Bernoulli equation by rho. Okay, for this case, I want to multiply by rho. What should I get? I will get the pressure plus rho V squared over 2 plus rho Gz equal to constant. So from here, I want to introduce you the concept of stagnation. Okay, let's say we have the ball and then we have the flow. And this is the fluid particle. What do you think when it hits the ball, it will stop? Okay, it will stop. And it will accumulate. Okay. A lot of particles accumulate, hitting one to each other. What do you think of the pressure? Increase or decrease? The pressure of at this point. at this stagnation point. When someone, okay, try to move in the bulk of the things, okay, try to move in the same in your direction, and then you will feel very high pressure, right? So this considered as a stagnation. Of course, the pressure is very increased. Okay, pressure is increased because you have a bulk of pressure, a bulk of fluid particle, okay, hitting you. So the pressure feel by the ball is increased. All right. So this one, the P here, okay, the P here is we call a static pressure. You will feel this pressure if you were moving along with the flow. That means this is you moving together with the flow. You will feel the static pressure. Okay, that means it's quite simple. Just imagine you yourself now. Okay, you are surrounding by the atmosphere. The atmosphere, okay, this is you. You are in the atmosphere, exposed to the atmosphere. The atmosphere, P ATM, have the pressure, yeah, 101.325 kilopascal. This pressure hitting you in every direction. But you cannot feel lah, because the pressure inside your body is much more than the atmospheric pressure. Okay, but we have the pressure. We call as atmospheric pressure. This is what we call a static pressure. That means the pressure static on you. Okay. In this one, in this part, okay, this is we call a dynamic pressure. Rho V squared over 2 is a dynamic pressure. Okay, it is represent pressure rise, pressure increase when fluid is brought to a stop. Okay, that means in this way. Okay, how to explain ya? Okay, for example, you are at the mountain, on top of the mountain. This is you. And then there is the wind speed. Okay, of course you are exerted by the static pressure. Okay, because of PATM. Okay, you have the static pressure. It is a very small pressure because the pressure is already there. Exert you. Static pressure. So this static pressure we call as a P. The dynamic pressure on the other hand is the wind. The wind flow. And suddenly hitting you. You will experience the pressure from the wind because the wind speed suddenly stop. Okay, this is at the stagnation point. Stagnation. So this is we call a dynamic pressure. Okay, by this one. So of course, the velocity at here, velocity 1 and velocity 2 is equal to 0. Right. So pressure at 1 and pressure at 2. Pressure at 2 is higher, very high. So the question will ask you find the stagnation pressure. So now P2 become stagnation pressure. Why? Because it is at the stagnation point. So we can apply the Bernoulli equation. Remember that this height H1 and H2 is the same. So again we can apply Bernoulli equation P plus rho V squared over 2 plus rho GZ 1 equal to P2 plus rho V 2 squared over 2 plus rho G Z2. This can cancel. Velocity at point 2 cancel. It will become, we need to find P2. Why P2? Because P2 now becomes stagnation pressure. The height in pressure. Okay. You will get P1 plus rho V1 squared over 2. So, in order to get the V as well, in order to get velocity 1, you need to know the velocity at 1. It is simply rearrange the equation. You will get 2 P2 minus P1 over with rho. Okay, that's it. That is the... Alright. So, can imagine 3 different pressure by holding up your hand in a steady wind. Okay. So, in this case, a static. Okay, static pressure would be atmospheric. This is I explained before. Atmospheric pressure, which is P ATM. Okay. The larger pressure feel at U, okay, due to stagnation point, stagnation pressure, okay, is a dynamic pressure. Okay, and okay, the larger pressure here. Alright. And dynamic pressure also considered as a build-up pressure. Okay. The last one before we end the class. Okay. A Pitot tube is inserted in an air flow to measure the flow speed. The tube is inserted so that it is point upstream into the flow and the pressure sensed by the tube is the stagnation pressure. The static pressure is measured at the same location in the flow using a wall pressure tab. If the pressure difference is 30 mm of mercury, determine the flow. Alright, I draw to you the Pitot tube. Okay. In the meantime, let's figure out how the Pitot tube works. Okay, this is the Pitot tube. Okay, we have the airflow in this direction. And then the gamma of air here is 1, 1, 0.8 Newton per meter cubic. This is filled with mercury, yeah. Okay, we have the mercury. Let's say the mercury color, this one. Okay, the grey. Okay, the mercury. The density of the mercury is 13550 kilogram per meter cubic. Okay. So the question asks, what the question asks? Determine the flow speed. That means V. V1 or V2? Of course V1. Okay. Okay. V1. Alright. Okay, only V1. So the question asks, find V1. So we can use this one. Right. V1 equal to square root of 2 multiply with the P2 minus P1 over density. So we can apply directly. In order to get the V1, which is 2 multiply with P2 minus P1 over with rho. Remember that the pressure at 2 is considered a stagnation pressure. Okay. So, our case now, we need to find the P2 minus P1. So, in order to get the P2 minus P1, the first, we need to use the manometer measurement. Alright, this is manometer, right? Okay, we can do the calculation from here until here. And then let's say this is our reference line. Okay. And it is given basically the distance from here to here is 30 mm. Okay. 30 mm mercury. So, do you still remember how to use the hydrostatic equation for the manometer measurement? Remember, manometer consists of the tube. Okay. So, the Pitot tube on the other hand is represented by this. Okay, why it is Pitot tube? Because the area here is very, very small. It will cause the velocity reaching at this point to stop immediately. So, V2 equal to 0. Okay, because the area is very small, you move at very high speed. And then you want to enter the small area. What do you feel? What do you think? Definitely, the velocity is very small because of high resistance to enter the small area. That means the velocity at that stagnation at small area is equal to 0. Okay, and V1, of course, we need to find. Due to the pressure, okay, due to the velocity is very small, the pressure is very high. So this high pressure will tend to push. Okay, P2. Okay, this stagnation pressure here, try to push this liquid of mercury. That is why you can see the difference in elevation. Alright. So, that means the pressure at stagnation point is equal to P2. So, this is P2. This is P2. Yeah, P2 acting here, down. And then, we have the pressure as well. Okay, at P1. So this pressure at 1, this is air. Let's say this is the same as here. Pressure 1. Okay, because this is exposed to the air only. So how to calculate? Okay, again using hydrostatic equation. Okay, we start from here, finish here. Okay, so P1 from here you go to here. So this is okay. So P1 minus P2 or P2 minus P1? Do you still remember the hydrostatic equation applied to manometer? Class? It is P2, right? P2 minus P1. P2 minus P1. Okay, if you want to go from here to here, the final minus initial. P2 minus P1. Alright. And then equal to negative. Okay, negative gamma Z2 minus Z1. So, P2 minus P1. You can see it is the same here. P2 minus P1. If we get this term, we can substitute directly. So, negative what? Gamma. Gamma of mercury. Gamma of mercury is, okay, which is rho mercury gravity. So, rho is given 135, okay, 50. So, multiply with the gravity, which is 9.81. Z2 minus Z1. Okay. What is the value of Z2? Class. I want to test your understanding. Z2 equal to what?
0.
0.
Okay, why 0?
Reference point.
At the?
Reference line.
Yes, perfect. You can see I said initially this is Z2. This is Z1. 0 minus Z1 equal to what?
30 mm.
0.03.
Yes, perfect. 0.03. Must use SI unit here. Okay. So you will get here. You solve everything completely. You will get 3987.77 Pascal. So in order to get velocity at the stagnation, okay, velocity 1 or this velocity here 1, yeah. Just substitute 2 multiply with 3987.77 over with what? Over with the rho of air. Rho of air basically is the gamma of air divided with gravity. Okay, so rho of air given 11.8 divided with 9.81. You get 81.4 meter per second. That is the final answer. Okay, class, are you clear about this? Any question? Alright. When you have a question regarding the Pitot Tube, okay, and there is a flow, you can see there is a velocity, there is a pressure, and there is an elevation. Please remind that, oh, this might involve Bernoulli equation. Okay, and then in the Bernoulli equation, you can look at, oh, these have the tube. Maybe we can use manometer equation. We can use the hydrostatic equation. From hydrostatic equation, we can relate back to the Bernoulli equation. This is something we call a complex thinking because you have the combination of prior knowledge, which is the manometry measurement. You measure using the hydrostatic and then you apply to the Bernoulli equation in the stagnation point. Okay. I think that's all for you up until today. For your test one, okay, I will confirm back whether it is until Bernoulli or not. Okay, I'm worried that the test might change lah. The test topic might change, but please prepare. It is 23, right? 23 of November. Okay, you only have 12 more days. Okay, please study and understand. If you are not understand, discuss with your friend or you can watch my video recording as well as refer to the textbook, right? I will share to you the tutorial I have done, the how I solve some question pertaining to this topic. Okay, I think that's all. Any question before we end?
No, Doctor.
Okay, thank you. Okay, I think that's all. Thank you very much for your time. I end my session with Assalamualaikum warahmatullahi wabarakatuh.
Doctor,
Yes?
can I have attendance again?
Okay, sure.
Thank you, Doctor.
Okay. Okay, welcome.